So we're looking to find the standard deviation in this particular case, and the standard deviation is just a measure of spread from a centre. So the first thing we've got to do is find the centre of this distribution, and we've got the numbers 1, 2, 3, 4, 5. And what's really nice about this question is, of course, they're all equally spaced, so therefore, in fact, the median and the mean are in exactly the same place. So you can see that 3 is my mean. But just to check it out, if I do the sum of all, and we use the x value, so it's going to be 1 plus 2 plus 3 plus 4 plus 5. And obviously we know that 1 plus 2 gives me 3 plus 3 gives me 6, 10, 15. So that's going to be 15. And I divide that by 5 because my mean, and we quite frequently use an x bar notation, is the sum of the x over the number I've got. So it's 15 divided by 5, which gives me 3. As I said, I could see from the information I'd got that it was straight away working okay there. Now, standard deviation, we want to know how far spread out from the mean is. So I would, in this particular case, probably draw up a table. And I've got my values 1, 2, 3, 4, 5. I'm going to do x minus x bar, the difference between my value and my mean. So it's going to be minus 2, minus 1, 0, 1, 2. And I can see the total of that is absolutely nothing, which doesn't help me. All right, so what I do in order to get rid of my negative signs is I square the whole lot. So I get 4, 1, 0, 1, 4. And this one's only symmetrical because of the numbers that were chosen in the first place. Last time I checked, 4 plus 1 gave me 5, plus 1 plus 4 gives me 10. So the sum of the x minus x bars is 10. And I want the average spread. So what I've got to do is I've got to, and we tend to use a whole variety of different notations, but because we squared, we need to square root later on. So our standard deviation in this particular case, I'm just going to use, well, I'm not even going to use SD. I want the sum of the x minus x bar all squared divided by the number I've got. So I've got 10 divided by 5, which gives me 2. Now that's technically the variance, and this question asks for the standard deviation. Notice I said because I squared it to make it easy, my standard deviation, I've got to square root it. Okay, so I want the square root of 2, and that is my standard deviation in this particular case. So there's my answer, square root of 2. So if I want standard deviation, what I really want is the square root, it's a rubbish square root, of the sum of the x minus x bars all squared divided by the n. That's my standard deviation formula, and these are the steps I've gone through. Now, the idea of tabulating it is to make it look a bit more obvious. There are different ways of doing this, but if I've only got a small amount of raw data, that is probably the most interesting or the most straightforward. It's not a bad idea to put it in a table just to make it clear exactly what you're doing.
The standard deviation is a measure of the spread of a distribution. We'll have a look at how it changes the look of a distribution later on. But one of the interesting things that comes out of the solution to this problem was that when during the solution, when we looked at the sum of x minus x bar, then that was 0. And incidentally, x bar is often used for mu, so they both mean mean. Now, in a way, this is sort of obvious because we get the mean from adding all the numbers up and then dividing by however many we've got, the numbers above and the numbers below cancelling out and so on. But it's worth having a quick look at this. One thing is that this actually is the sum from I equals 1 to n of all the values. And what that means is we can split this into, so we'll just ignore that for the moment, and we'll say that that's equal to the sum from I equals 1 to n of xi, take away, now for the x bar, that's the same for each value of I. So, when I is 1, x bar is x bar, when I is 2, x bar is x bar, so we get n x bars, or n times the mean. Now, since the mean is the sum of the values divided by n, then that means the sum of all the values is n times the mean. So this gives us n times the mean there. And n times the mean, take away n times the mean, is indeed 0. So, what you're shown in the question, and you probably already knew, is that what we do with this is we square them. Because what we need to do, when we've got these 5 numbers, minus 2, minus 1, 0, 1, and 2, is the problem is that the negatives cancel out the positives. So if we can make them all positive, then that solves the problem. But actually, there's another way of making them all positive. So we could square them, which is what we've done in the question. But we could take the modulus. So then we'd get 2, 1, 0, 1, 2. And there is an alternative way of measuring spread by using the modulus. There are various mathematical reasons why the usual definition, which is the one you've been taught for the variance and then the standard deviation, is used, but it's quite an interesting history, in fact, and there's an interesting article on it at this website for those of you who have an interest in stats. Here we can see a curve of a probability distribution. So the area under represents how much of a certain value or between certain values there are in the distribution. This is a normal distribution which you'll come across in A2, but there's a few interesting features here. First of all, this shaded area is one standard deviation either side of the mean. So here we start with the mean as 0, the standard deviation is 1, and what this shows is that if we go for the mean plus one standard deviation that side and the mean minus a standard deviation that side, then we get this proportion of the overall distribution. The sum underneath the whole thing is 1, so the integral of this curve between minus infinity and plus infinity is 1. So we see that there's roughly 68% contained between the one standard deviation below the mean and one standard deviation above the mean. So in terms of a measure of spread, if we increase the standard deviation, that means it's more spread out. So we can see that happening. Just go up to 4. And so now we can see we've still got this 68% here, but it's, now you have to go from minus 4 to plus 4 to get 68% of the distribution. Now, we can also go smaller than 1, and as you might imagine, this just makes it more and more pointy. It goes. still, now we're at the standard deviation of 1/2, if we go from -1/2 to +1/2, we'll still get 68% under the curve. Anyway, leaving aside this 68% business, the point is that with a smaller standard deviation, the numbers, the values are much closer to the mean. With a bigger standard deviation, they're further away. We can, of course, just move this along, and you'll notice nothing changes about the curve. The centre of the curve changes, so now we're at a mean of 3, so the peak of the normal curve is there. Still got your 68%, one standard deviation above, one standard deviation below, but the overall shape doesn't change. So that's just a little look at how, really, the focus of this was how increasing the standard deviation shows that a larger standard deviation means that the values are more spread out.